So I want to talk about a very interesting classifier structure. In this case, talking about what is a vector matrix multiplier and what is a WTA, or winner-take-all, type of classifier combination. So sort of in a single layer. And in fact, typically we'll talk about this as a K winner-take-all in general, although today we're going to really just talk about it as a single winner case for most of this conversation. And so when you look at this, what do I mean by this? Well, basically it's going to be a single input vector, a single vector matrix multiplication, so has a very simple product that you would expect. And then that goes into a winner-take-all block, which could be now a single winner, multiple winner type of winner-take-all. It could be a local winner-take-all, local winner, so you have some sort of spatial sort of structure to it. It could have hysteretic kind of things, so there's sort of temporal dynamics. Winner-take-all structures have a lot of richness to them, but even if I just take a very single winner-take-all for the sort of simple classifier structure, there's a lot we can already see about this, and all these pieces and parts really open up the richness of what's possible. What's interesting about this function is you go, well, with a single vector matrix multiplication with a single winner-take-all layer, I can get a universal approximator. This originally came from some early sort of thoughts around that Wolfgang Mass had thrown out, very much sort of theoretical, which was incredibly appreciated, not necessarily constructive, which was the interesting part. And was we started to look at this question in how do we actually do simple classifiers? There was a whole neuromorphic reasons we were looking for this, and wanted to see how far this got, because as you start putting this together, you realized putting a VMM plus a winner-take-all classifier had some very interesting potential, but we couldn't quite put our finger on it at first. Sort of found this conversation and went, well, that's interesting. Could we actually use that to construct an exclusive OR network? Why an exclusive OR network? Remember, that would be the classic thing that showed you need two layers to do a neural network structure. So if you do that in one layer, all of a sudden now, you have different things. And it was, by the way, it's not hard to show that this structure will do a hyperplane classifier, so no question there. You can do that plus the XOR, you've now opened up the opportunity. Well, it turns out that such a block would look like this, and it turned out this starting point we looked at saying I had a 3-input VMM to begin with, 3 by 3 to start this. There's different ways you can improve this with particular weights of 2 and 1. And 2 off of this sort of constant term. Things can get collapsed and we can play with this, but this was how the original structure happened. Because you have this interesting point, if you look at the decision space between x1 and x2, you have these decision boundaries that say, I'd like to have one result for these two outside edges and a whole different value in the middle. And you think to yourself, wow, that's can't be done in a single hyperplane. So what you end up doing is you're able to sort of almost create two hyperplanes and then look at a competition between them. And that is actually what starts to help, is that you end up saying, well, let me look at these frameworks, and what I end up getting is I can create hyperplanes around the x1 and x2, but I can also say, hey, I've got one thing sitting at sort of a middle, there's almost sort of a sort of critical point here, and then 2 points on the outside edges. These are now my 3 critical points, which is why I use this for the 3 VMM. And all of a sudden now that kind of forces 2 boundaries in between. So as a result, you say, well, what would happen if I measure it? Well, you actually do these measurements, and what you find by looking at the x1, x2 plane is, in fact, I get a whole region which is high here and low on the 2 edges, which is, in fact, shows you the exclusive OR. You can actually get this with a 3 parity. You can also get this with a 4 parity. And at that point, it's pretty much generalizable all the way up. It's pretty cool because you can use this for a whole range of different classifiers. It's really useful because particularly where you might think I have to have 2 layers or more to make a function work, it can be done in one. Does that mean that you should always use one? Well, there may be multiple reasons you use multiple layers. But it's incredible that you can already do it with one. And that gives you a huge opportunity, particularly when you're doing embedded type of structures where efficiency is absolutely critical in the systems that you're building.